Yeah, thanks for the introduction. So it's a pleasure to be here to talk, to give this lecture on vector commitment. So I'm Dario Fiore. I'd like to start with just a few words about myself so that you know who I am. So I'm an associate research professor at IMDEA Software Institute in Madrid, which is a research institute in computer science based in Madrid in Spain. I did my PhD in computer science at University of Catania, and then I was a postdoc at ENS Paris, the New York University, the Max Planck Institute for Software Systems, and then I moved to IMDEA as an assistant professor and now as an associate professor. So my research interests are on cryptography and in general its applications to security and privacy. And some of the topics I work on include zero-knowledge proofs, commitment schemes, and also computing on encrypted data. And as part of commitment schemes, I'm very interested in actively researching in vector commitments. So okay, so let's start with the with this lecture, and I'd like to start by giving with a motivation, with a motivating application for this topic. And the problem I'd like to start is that of outsourced storage. So in this problem, we have two main parties. There is a server, think of it as a cloud server, and there is a client. And the client is the very small device and wants to outsource the storage of a large database to this cloud server. And he outsourced the data at the server. And one of the first questions that the client may ask is, is the server still storing my data, right? And another question that can ask is that at some point, right? So he wants to retrieve some parts of the data, think that he wants to get the ith record of this database. He gets the answer from the cloud, and he asks, okay, is this correct? Is this the same data that I gave to you? And these questions are not trivial to be answered if the device has deleted the data, right? So if the device keeps the data, of course, he can compare, but clearly the device didn't want to store this large database. So one important requirement that makes these problems even more challenging to achieve is that we would like to find solutions where, in order to guarantee security, the communication and the storage of the device, this solution should be constant size. So essentially, the communication should not depend on the size of the database. Of course, this after having outsourced the database. Once the database has been outsourced, then we would like to work in constant size. Okay, so and we'll see how to solve this application using vector commitment. So now we will start more formally into defining first of all, what is a commitment scheme, and then later we understand what is a vector commitment. Okay, so cryptographic commitments are a very fundamental primitive in cryptography, and they can be seen as the digital analog of a safe box. So in the following sense, so I think that here we have two users, Alice and Bob, and Alice has a message M, and when she wants to commit to the message, she puts the message inside this safe box, right? So, and she sends the box to Bob. And then at a later point in time, a commitment has the possibility to open this commitment, this safe box. And opening essentially means to have a claim by Alice that says, oh, it's M, that the message M that is inside the box. And she can send along a key. And this key can later be used by Bob to open the box and get this message M. Okay, so that's the idea. For now, I'm staying very high level. So that's the idea of a commitment scheme. And now let's see what security properties we want from a commitment scheme. So the first property is what is called ID. And the idea is that Bob learns nothing about the message M until the moment Alice gives him a way to open the box, right? So until the box is closed, Bob has no clue about what message is inside. And then the second property is binding. That means that Alice cannot change her mind about n. So, in this picture, this means that if Alice has put m inside the box, then cannot later claim that it was a different m prime message inside the box. So in some sense, we want that it should be hard to open the same commitment at two different messages, to kind of explain it and kind of cheat in the sense of giving two messages and making Bob believe that there was a different message inside. Okay, so let's now be a bit more formal. I'm going to present what's exactly the notion of commitment scheme in terms of algorithms. Okay, so a commitment scheme consists of several algorithms. So first of all, there is a setup algorithm that, given the security parameter k, produces a commitment key. So this key is public to everyone. Think of it as some public parameters. And then using this key, you can run the commitment algorithm on input a message x and some randomness r. And given this, you produce a commitment that we denote with C. And then given the same input, meaning the same message x and randomness r, you can also produce an opening proof. So that's the open algorithm. And the idea is that this proof can be verified using another algorithm, which is the verification algorithm, that takes the commitment, takes the message, and takes the proof, and gives you accept or reject. And here the idea is that, like, you can essentially check, can be convinced that X is the message inside C. So in fact, the basic property that we want from commitment schemes is correctness. So correctness is kind of the easy property that says that if you commit to X using randomness R, right? So and then you create an opening for the same X and the same R, then this commitment and opening should be accepted by the verification algorithm, right? So there is this, if you input the verification algorithm with the output of the commitment algorithm and the output of the open algorithm with the same X, then the verification should accept. The next property is binding. So here the usual cryptographic, the cryptographic formula is to define binding, is to define it to say that if you take any adversary that runs in probabilistic polynomial time, and we consider any honestly generated commitment key CK, then we want that the probability that the adversary produces a commitment C and then two values X and X prime, along with two proofs pi and pi prime, that are both accepted by the verification algorithm. So, verification accepts X and pi under C and X prime, pi prime under the same commitment C. And if these X and X prime are different, then there is an attack. So, and we want to say that the scheme is binding if the probability that any polynomial time adversary produces a tuple that satisfies these conditions is negligible. Okay, so that's I'm assuming that everybody is familiar with the way cryptographic definitions are formulated. But essentially, really, this is just saying that you cannot have an adversary that produces one commitment that is open in two different ways and into two different messages. And then the last property is hiding, that intuitively says that you cannot understand if the commitment is created to X or to some other message X prime. More formally, we say that hiding holds if for every probabilistic polynomial time adversary A and every pair of messages X and X prime that are different, you cannot distinguish the output of com computed on X and some randomness R from the output of com and value X message X prime and randomness R prime. Okay, so now that we have seen what is a commitment scheme, I now can explain what is a vector commitment scheme. So vector commitments are a notion that we propose in a work joined with Dario Catalano back in 2013. And the very basic idea is that it's a way to commit, instead of committing to single values, to commit to a vector, but with some special property. So we would like to commit to a vector V, so which is an ordered sequence of values, V1, V2, Vn. So it's V now what we put inside the safe box. But then the crucial property is that instead of opening the box in full, we want to open only like selected entries of the vector. So in the sense that Alice can now produce a key to only open position I. So she can produce this key for position I, give it to Bob, and then Bob can be convinced that Vi is the ith entry of the vector inside the box, but this information may not necessarily tell Bob what are the other messages, so what are the other values of the vector. And vector commitments have two key properties. One is position binding. So this is an extension of the binding property of commitment schemes that says that Alice or a malicious party cannot open the same commitment to two different values, but at the same position. So and we'll see this more precisely. And then the other property is succinctness. So this is another property that makes this notion non-trivial to realize. And succinctness says that the size of the commitments and the size of these opening keys or opening proofs is short. So in the sense that it does not depend on the length of the vector. Okay, so let's see more precisely what does it mean to have position binding. So assume that there is here an attacker and then the honest verifier Bob, and the attacker has produced some commitment. So think in pictures that he has given to Bob this safe box. Now a successful attack is one where this attacker is able to create two different opening keys that one is for position I and value Vi, and the other one is for the same position I, but for a different value V prime I. So if Bob would use successfully both keys to, just to get them accepted, then this would be an attack, because in some sense that you have managed to convince someone that in some position there are two different values, which is something that should not be possible. And in terms of succinctness, really here what it means is that when you produce the commitment, so the size of the commitment, the size of each opening does not depend on the length of the vector, so that we denote by n. And note that succinctness is a crucial property because if we drop it, so if we consider, let's say, vector commitments without these succinctness properties, then we can easily construct them by just concatenating commitments, or one commitment for example, for every VI. So if we concatenate different commitments, that we would build a vector commitment, but of course, the size of the commitment would be, for example, linear in the vector length n. Okay, so now I want to give you an algorithmic description of vector commitment, so that we can be more precise. So in a vector commitment scheme, the first algorithm is the setup algorithm that, in addition to the security parameter k, can also take an upper bound on the sides of the vectors that we are going to commit. And the output of this algorithm is a commitment key. Again, this is just public information. Oh, sorry, there is a... Yeah, no, the animation it was wrong. Okay, so the second algorithm is the commitment algorithm that takes as input the commitment key and the vector and produces a commitment C. And then there is an opening algorithm that, given the commitment key, the vector, and some position, produces an opening proof for position I. And then there is the verification algorithm. And this verification algorithm is similar to the one for standard commitments, but the difference is that it takes also as input a position I. So to sum up, it takes as input the commitment C, the position I, some value Y, and an opening proof pi I, and it outputs accept or reject. And the idea is that if it outputs accept, this means that Y is the value at position I in the vector that was committed in C. And in fact, that's what the correctness property says, that if you commit to the vector V, and then you open the same V with position I, and you check it for position I and value VI, then you should get an accept. One thing before I move on, I want to notice is that I have removed, compared to the notion of standard commitments, the use of randomness. The reason is that, in vector commitments, it could also make sense to have commitments that are deterministic and where we don't have the hiding property. In fact, so we will not consider hiding property for vector commitments. I mean, I can expand this if you have questions about it, if you want. Okay, so, but the main security property of vector commitments is position binding, and the cryptographic definition of position binding says that for every probabilistic polynomial time adversary A and any commitment key that is honestly generated by setup, we want that the probability that the adversary produces a commitment C, a position I, and two value Y and Y prime, along with two proofs pi and pi prime, that are both accepted. So, we accept Y and pi for position I and commitment C, and we also accept Y prime and pi prime for position I and commitment C. And if Y is different from Y prime, right, so that's the winning condition, then we position binding holds if the probability that this happens is negligible, right? So something very small, let's say close to zero asymptotically. And finally, the other property that is more like a functional, it's an efficiency property, in fact, is succinctness, that says that there is a fixed polynomial P in the security parameter K, such that we can bound every honestly generated commitment and opening proof by P of K. And that's a way to formally say that the size of the commitment and the size of the openings do not depend on the size of the vector that we commit to. All right. Okay, so now I want to go back to the our motivation, which was that of finding a solution to security of outsourced storage. And I'm going to show you how we can use vector commitments to achieve this. And in particular, I'll show you how to solve the second equation, which was, how can we be sure that the records we retrieve from the cloud are correct? Okay, so let's start from the beginning of the problem, where there is the client that has this large database. Now, when the client outsources the database, we think of the database as a collection, so it's a vector. So this is not difficult to do. We can think that database is a sort of collection of items, of rows, for example, and we can model them as V1, V2, Vn. And so what it does is to commit to this vector. Then he sends the database to the cloud and actually deletes it from its main memory. But then at a later point, the client wants to use the data. It does not have it anymore. So he's asking the cloud, can you send me the ith record? So what the cloud can do at this point is to run the opening algorithm, right? So you also can see the database as a vector V, and if it's asked to provide the VI value, is creating an opening proof for position I, and then he's sending to the client VI and the associated opening proof pi I that he produced using the vector commitment algorithm. And this way, the client can run the verification algorithm to on input the commitment C that is the only thing that is storing, the position I, the value VI that it got from the cloud, and this opening proof, and is going to check if the result is accept or reject. So why this is a good solution? So first of all, in terms of storage and communication, we can see that once the database has been outsourced, the only thing that the device is storing is a commitment C, and by definition, the size of this commitment is some fixed polynomial in the security parameter. So it does not depend on the length of the vector, which was the size of the database. And also, whenever it retrieves a single record, he only gets, in addition, this opening proof, and the size of the opening proof is also independent of the database size. So that's why vector commitments give a solution for secure outsourced storage in terms of efficiency. Now, in terms of security, the reason, at least an intuitive reason, I will not give a formal proof of this. The reason why the cloud server, a malicious cloud server, cannot cheat and convince the client of false values is that in order to cheat, the server should produce a valid opening proof for some data which was not the one that was originally committed by the client. But that means that it should be able to come up with a valid opening proof for that. But we know that there is also a valid opening proof for the correct value VI. So, the existence of these two proofs would break position binding. So essentially, the position binding property of vector commitments is what makes this protocol secure in terms of protection against cheating cloud servers. Okay, so however, secure outsourced storage is not the only application of vector commitments. There are many more that I will not describe in this lecture, but I want to give you some pointers. So one is that of proofs of retrievability, or so-called proofs of space. So this is essentially, it's a problem related to outsourced storage, and is related to the first question: how can you check that this remote server is storing your data without necessarily retrieving it? And this is, for example, used a lot both in cloud storage, outsourced cloud storage, but also in blockchains based on proofs of space instead of proofs of work, such as Filecoin or Kia. And a second application is to stateless blockchain. So, for example, the Ethereum blockchain, which is account-based, where there is essentially the state of the blockchain consists of account values for every user. Like for every user, you have a memory space where you store, for example, the amount of coins that the user has. So this information can be modeled as a vector, and therefore, in order to keep a concise representation of the state of the blockchain, you can use a vector commitment for it. And then there are also cryptographic applications, such as the vector commitments can be used to construct succinct arguments, zero-knowledge sets, accumulators, and many more. So I have a list of references at the end of the presentation where, for example, you can find pointers to these applications. So, so in the second part of the talk, essentially this last, I think, 5 minutes or a bit more, I want to give you an idea of how we can construct vector commitments. Before that, I'll first describe what's the state of the art. And the first thing I want to mention is that there is this famous construction that are called Merkle trees. That is a way to hash data in a tree fashion that can be seen as a vector commitment, but with the difference that the size of the opening proofs are logarithmic in the size of the vector instead of being constant. So the notion of vector commitment was implicitly proposed in a work that we published in 2008 with Dario Catalano and Maria Grazia Messina. And there we call it like n-traptor mercurial commitment. Was a more sophisticated notion, but essentially vector commitment was a special case of that, but we didn't have a full construction for it. And a full construction of essentially of this primitive, this entraptor mercurial commitment was proposed in 2010 by Lieber and Jung, based on groups with pairings. And then what we did in this paper in 2013, this CF13, was to first formalize the notion, like in full, and then to propose constructions based on the RSA problem and the computational Diffie-Hellman problem in bilinear groups. And in general, nowadays, in the state of the art, we have several realizations of this primitive based on either groups of unknown order, groups with bilinear maps, or also lattices. So what I'm going to show you in these last 5 minutes is a way to construct vector commitments in groups of prime order with pairings, and based on the computational Diffie-Hellman problem. So this is a very simple construction. But this is probably the most technical part of the presentation. So let me first introduce what are bilinear groups. If you don't know them, so we say that bilinear groups are tripole of groups G1 that we denote with G1, G2, and GT that have the same prime order Q, and that are equipped with a bilinear map E that goes from G1 and G2 to GT, and this map must be efficiently computable, non-degenerate. This means that for every pair of generators G1 and G2, the map applied to the generators should not give the identity in the group GT. And then it should be bilinear. So that means that if you, for example, apply the map E on G1 to the power of A and G2 to the power of B, this is the same as applying it to G1 to the power of B and G2 to the power of A, which can also be seen as taking the map on G1 and G2 and exponentiating the result to A times B. Okay, so that's the main tool, and that's especially the bilinear property is a key property that we are going to use to construct vector commitments. Okay, so how do we create a commitment key? So that's if you remember, it's the first thing, and that we have to do, and this is for commitment key for the vectors of length n. So what you do is to first sample two random vectors that we call alpha and beta. So these are vectors of length n and in ZQ. And then we compute the key that consists of the following elements. So we compute elements AJ that consist of G1 to the alpha j, and BJ that consists of G2 to the power of beta j. Okay, so essentially we have n group elements in G1 and n group element in G2. But then we also add additional elements that are what we call HIJs, that essentially consist into publishing G1 to the alpha I beta j for all indices I different from j. So this is very important. We're going to see it's very important for security that we never publish G1 to the alpha I beta I. Okay, so how do we commit to a vector V? So it's a very simple way to do the commitment. So we compute a multi-exponentiation that consists into taking the product of AJ to the power Vj. Okay, that's a single group element that we use as a commitment. Okay, the more sophisticated part is how to do the opening. So to open the commitment at position I, we create a group element that we call pi I, which is the product of HJI to the power of Vj for j different from I. Okay, so essentially it's again we are notice that we are excluding the case j equals I, for which we wouldn't have the element H, let's say JJ or II, right? And we are exponentiating to all the elements of the vector except the ith one. And now, in a second, we're going to see why this works. But first, let's see what is the way we verify, and then we see how it works. So verification essentially is a simple pairing equation in which on input the commitment C, we apply the bilinear map E on the commitment C and the value BI from the commitment key. So if we're verifying for position I, and then we check that the result of this map is equal to the result of the map applied to the opening proof by I with pair with the generator G2 times the map on AI BI to the power of Y. And Y is the value that we would like to test if the ith value of the vector. So why correctness works? So and this will explain you also what is the rationale of the construction. So let's start with the element the map, the first the left-hand side of the pairing of the verification equation, which is the map applied on C and BI. And let's develop what is the commitment C, right? So actually C, if we consider the way the AJ values are created, is G1 to the power of the sum of alpha J Vj. Okay, so this is just the, we applied how the value AJ are built. And then BI by construction is G2 to the beta I. Now we can apply the, notice that by applying the bilinear property, we can take this sum out and beta I, so we can multiply the sum by beta I, and we can take it outside the map, so we can write everything as the map up on G1, G2 to the power of the sum for J of alpha J beta I Bj and plus alpha I beta I Bi. So essentially here I'm explicitly taking out from the sum the ith term that I'm denoting in red. And then we can continuing to look at this sum in the exponent, we can apply again the bilinear property and just take the green part inside to the exponent of G1, and we take the rest of the sum in a second pairing, right? So I just now splitting the alpha I Bi Vi in this way in the red term of the map applied on G1 to the alpha I, G2 to the beta I, everything to the power of Vi. And here I'm only using the bilinear property of the map. And now we can see that each of these terms respectively corresponds by construction to the pairing of pi I and G2 and the pairing of AI Bi and to the power of Vi, which is supposed to be the value Y in the correctness requirement. Okay, so I mean this may need some time to be digested, but that's essentially the idea of the scheme. So a few words about the security, because I'm seeing that I'm running out of time a little bit. So the security of this scheme relies on the hardness of the computational Diffie-Hellman assumption in bilinear groups that says that every polynomial time adversary that takes as input G1, G2, G1 to the A, G1 to the B, and G2 to the B for random AB has negligible probability of computing the element G1 to the A times B. So this is essentially a variation of the standard computational Diffie-Hellman assumption in bilinear groups. And essentially the theorem that guarantees security says that if the CDH problem is R, then the position binding of the vector commitment that I described holds. Yeah, maybe I'll keep the idea of the proof only for if there is interest for questions, but what's the rationale of making this proof is the idea that we have to find a way to use an attacker in order to an attacker against the vector commitment in order to build a solver for the computational Diffie-Hellman problem. Okay, so I'll skip this slide and I'll go to conclusions, and then I'll be happy to take questions. Okay, so what I presented in this lecture is the notion of vector commitments, right? So, which is this idea of committing to vectors of elements with the unique feature of opening single positions of the vector. And then, and this comes with two crucial properties. One is succinctness, that is an efficiency property that says you cannot, that the size of the commitment and the size of these opening proofs do not depend on the size of the vector. And then there is position binding, which is a security property that guarantees that you cannot convince someone that there are two different values at the same position in the committed vector. And we have seen how this notion of vector commitments can be used to solve the problem of secure outsourced storage, both by giving us both security and efficiency. And I presented this construction based on the computational Diffie-Hellman assumption in bilinear groups. I want to conclude by saying that vector commitments are an active area of research, and in particular, the latest developments in this research area deal with the problems of building vector commitments with more advanced properties. For example, one of these properties is the idea of updating the commitments, so what is called updatable VCs. This means what if you have a commitment to a vector V, and now you want to change a single value of the vector, and you want to get a commitment to V prime, but without recomputing everything. And so, this is, for example, useful still in outsourced storage if you want to update the database, but you don't want to download the original database to perform the update. Another research line that started a few years ago is related to subvector openings, which means how to create opening proofs for many positions simultaneously and still have them of constant size. And also another property is aggregation, which means how can we have, let's say, an opening proof for position I, and another opening proof for position J. How can we create now an opening proof for both positions I and J without, again, having to know the original vector? And finally, really the frontier of this research area is the notion of functional commitments, which is an extension of vector commitments, where instead of opening to single values of the vector, you can now open to a function of the vector, right? So, for example, you can prove that the average of the values in the vector is a certain value. And yeah, with that, I conclude my presentation. I'll be happy to take questions. And in the last slide, you can find references to all the papers that I mentioned.